Hari Om. In this part, we discuss magnetic hysteresis. There is something related to magnetism of the material, and based on the hysteresis behavior, we can choose the material for different purpose. So let us see what magnetic hysteresis is. You studied magnetizing field and intensity of magnetization, and based on that we understood intensity of magnetization I vector is found to be directly proportional to the magnetizing field H vector, and I divided by H is equal to chi m also be found, and that chi m is called the magnetic susceptibility of the material. So now if I consider a ferromagnetic material and I try to magnetize that material for a complete cycle of magnetization. Complete cycle of magnetization means half of it is magnetization and the other half is demagnetization. Together it is called complete cycle of magnetization. Now when you do that complete cycle of magnetization for the ferromagnetic material and see the behavior of I and H, we will be getting a graph like this. Along the x-axis I take magnetizing field, and along the y-axis I take magnetization. Then, as a ferromagnetic material, initially it is not a magnet, and when I start applying the magnetizing field from the origin 0 to a value, as I go on increasing the magnetizing field, you can see that the magnetization also increases. According to mass, it must be directly proportional, therefore you will be expecting a straight line, slanted one. But in practice, it is found to be like this, that means initial case when you apply the magnetizing field, large amount of field is used for breaking the atomic dipoles loops there, or orientation must be in random, and those orientation must be made in a particular direction. For that, large amount of field is taken. So initially intensity of magnetization is very small, but gradually it is proportional to H, and then it reaches to a saturation level. By then, the whole atomic dipoles are aligned along the direction. So, no point in increasing the field further, therefore I stop. Now, from here I start decreasing the magnetization. Decreasing the magnetizing field. Start reducing the field back to 0. As I bring the field back to 0, we will be expecting that curve to come like this, but the curve starts moving like this. And as this is starting to come like this, that is, it is moving in another way, and you can see that when the magnetizing field is 0, intensity of magnetization is not zero. So there remains a part 2a. An amount of magnetism is stored in the material, and that measure of OA is called retentivity or residual magnetism or remanence for the material. Again, if I take the magnetizing field to increase in the opposite direction, what you can observe is that the graph will be that the remaining magnetism is found to be zero in this particular point. So when I apply a reverse magnetizing field, the retentivity is made zero. That measure of OB, the magnetizing field required for making the retentivity zero, is called coercivity. Coercivity. And again, as I increase that field up to the same amount back, what I can see is that the graph is going almost straight and coming to the saturation. And from there, I start reducing the field again. What I can observe is that the value of OA prime remnants and so when I make that magnetizing field zero back again, what I can observe is that when the field reaches zero, the magnetization is not really zero, that is some amount of retentivity is coming again. So always you can see we started from here, but the path is now not going in the same way, going in some other way. So if I continue this, I will be getting a loop of somewhat like this, okay, and this loop will be known as hysteresis loop. Hysteresis loop. Now, this is for a given material, you are getting a loop like this. This is the definite area for the loop you can define there. Okay? And when the material is subjected to a complete cycle of magnetization, continuously you can see that the material is getting heated up. That means there is an amount of work being done in this process. So amount of heat energy developed per unit volume of the material will be found to be equal to the area of the loop. Heat energy developed per unit volume of the material is found to be equal to the area of the hysteresis loop. So, if you get a large area of the loop, means there is a large amount of energy wastage is coming. Another point to be noted is that based on the hysteresis loop area, we can select the material for different magnetic purposes. For making the temporary magnets and making the permanent magnets. All those materials are chosen based on its hysteresis loop. One more point. Why the material is getting heated up while it is undergoing a cycle of magnetization? This is a fact to be known. See, inside the atomic dipoles are getting aligned. If the field is in one direction, alignment will be like this, and the field reverses, the whole atomic dipoles are to reverse its direction. So this requires an amount of work for the realignment, and that work is producing the heat output.